Okay, so this is 5.7 factoring polynomial functions. Again, what we're doing today is going to set up everything else we're going to do for the rest of this chapter. So you really got to focus in, and we've got to go through like 4 processes. So there's about 4 different things we got to look at and figure out and discern if we're going to end up where we want to. The first is the remainder theorem. Remainder theorem. The remainder theorem. It basically says this: for any polynomial p of x divided by a binomial x minus a, and that should look familiar, right? We're reading max and min values. We're just reading the value after the negative sign. Yields a remainder equal to, and capital P were functional notation, and where the x would normally go, put a red A. P of A. Okay, that probably doesn't mean anything yet, and that's okay. It should in a minute when we do an example. Okay, so let's do the example, then I'll come back to that and show you that again and try to make some sense out of it. Okay, so here's the situation, right? Right now we've got this function P of x equals 2x squared minus 7x plus 6, and we're going to divide it by this, x minus 2. So again, like we did with max or mins, we're going to do P of 2. So that's what we want to do. So to do P of 2, I'm going to put 2 in, and I'm going to do it in red everywhere where the x is, right? So I'm putting a red 2 in there, and I'm putting a red 2 in there, right? Everywhere where the variable is, we're putting in 2. So the next line, 2 squared is 4, and 2 times 4 is 8, so that's an 8. Negative 7 times 2 is a negative 14, plus the 6. And so when we're done, I'm going to use my red here for the 2. So this P of 2 ends up equaling, and in this case, it is 0. P of 2 equals 0. Okay, so what we're saying then is a polynomial divided by a monomial yields a remainder equal to P of A. What we're saying then is this, that this 0 is the remainder. That's what we're saying. 0 is the remainder. So to prove that, we need to do long division. You're not going to do long division in this step down the road. We're going to use this concept to save us from doing this long division. I'm just doing the long division to show you that the remainder is in fact 0. Okay? So long division, hopefully remember how to do it. Take the first 2x squared and divide it by the first, right? So again, we know a 2x squared divided by an x is a 2x. And I taught you guys to put the 2x in the x column, right? And remember, we got to distribute. X times 2x is 2x squared. And a negative 2 times a 2x is a negative 4x. Like any long division, you now subtract. The front is 0, but don't forget you got to distribute that negative sign. So you end up with a negative 7x, and a positive 4x is a negative 3x, right? Long division. And if you remember, we're bringing down our 6 now. And how do you figure out what else to put up top? Again, the front, the negative 3, or the negative 3x divided by the front, the x. And that's a negative 3, right? First term always divided by the first term. So a negative 3 goes up top. And so again, the x times the negative 3 is the negative 3x. And the negative 2 times the negative 3 is a positive 6. And when you subtract them, you get 0. And that's the point. We can figure out remainders this way. If you were to divide this binomial right here, right, into this polynomial right there, we know that the remainder is going to be 0. We could find that out by doing long division, or we could find it out by doing this. This is the remainder theorem right here, right? That part's the remainder theorem. By putting 2 in for the variable, we can figure out the remainder. That's what we're after. Okay? So that's first concept. Questions on that? Questions? Completely lost? Hopefully not. Okay. So let's keep going. All right, so then you might be given a question like this. Find the remainder when you've got this function, right? And it's divided by this value. Now, you can go the long way. You can do long division, but you don't want to do the long way because it's longer and it takes more time, and time is a premium when you do math. So we don't want to go the long way. We don't want to do long division. We want to use the remainder theorem. Okay, so to use the remainder theorem, what value should be used for x? And there's 2 ways of looking at it, right? Remember, in this situation, there is a plus sign there, right? Not a minus. So just like we did with parabolas, the first way to look at it right here, right, would be x minus a what? X minus a minus 1, right? That would be one way of looking at it. The other way to look at it, if you want to, is to just set this, the x plus 1, equal to 0 and solve the little equation. It's just 2 ways of looking at the same situation. If you were to solve it, what does the x end up equaling? A negative 1, right? There's just 2 ways of looking at the same concept. But again, you read the value of a when there's a minus sign in front. So we're going to do p of negative 1, right? And again, usually we're just thinking this way, coming off of max and mins and understanding what the max and min point was, we'd know that if there's a plus in front, then it must be minus the minus 1. If you want to treat it as an equation, set it equal to 0, that's fine. In either case, you end up at a p equal negative 1, and that's where you got to end up. You got to do p of negative 1. All right, go ahead and work that function and see what you get for a remainder. What is the remainder to this thing? Don't pay attention what I'm doing. I'm doing the proof again. I got an 8. It's your remainder 8. Okay. So if you did it the remainder theorem way, all right, you got a negative 1 there and a negative 1 there. Negative 1 squared is 1. 1 times 4 is 4. Negative times a negative is a positive. And sure enough, 8 is the remainder. And again, on the proof side, 8 is the remainder. Again, you will not be doing this. you will not be doing long division. I'm just showing you that the thing works. Okay, that's all I'm doing is showing you, hey, it's true. You really do get the remainder. Noah. Ask your question again. I didn't follow it.
Are you able to use the little question, the load equations for the same?
Not sure I'm following you. Are you saying, can you do this to find the solution, the remainder? This here? The reason I did that was to figure out that I have to use a -1 for the x. So if that's what you're asking, then yes, you can look at it that way. That, remember, is an or. You don't need to look at it that way. You can simply look at it that way. You're either going to look at it this way to figure out that you're doing p of -1, or you're going to look at it this way to figure out that you're going to do p of -1. Whichever way you want to look at it, those are just there to help you to know what to put in for the a value. Okay? And then you have to finish that function off to figure out what the actual remainder is. Any questions? Any more questions on that? So that's the start. All right, next. Back of your sheet, right? Okay, so here's one more question. Whoa, is that the right page? No, I'm way up here, that's why. All right, number 2. All right, so that was the remainder theorem. Now comes the, and this is green, factor theorem. The factor theorem. And this is really what we're after. We got to find factors. We got to find factors, and that's what we're trying to end up at. All right, so the factor theorem says this. Any given binomial, x minus a, is a factor, right? If when you do p of a like we just did, your remainder ends up being, any guess? When will it be a factor? If the remainder is, let me ask you here, I'll give you an analogy, all right? Just hold off a second. Let's suppose we have something like this. You don't need to write this. Let's suppose we had a 10. Is 3 a factor of 10? No, 3 is not a factor of 10. I'll keep my 10 there. Here, I'll do this. Is 7 a factor of 10? No. Is 57 a factor of 10? No. Is 2 a factor of 10? Is 5 a factor of 10? Why didn't 3 work, but 2 works? What's the difference when you do the division? What's the difference in the division when you divide by a 7 per se, or when you divide by a 2 per se, right? What's the difference when you do the division? Mitchell? The remainder is 0 on this one, isn't it, right? But you're going to get a remainder on this one, right? You're going to have a 3 remainder on that one. So things are a factor if when you do, for us, the P of A, if you end up with P of A equaling 0, all right? And that's what we're after. If we get a 0, then it's a factor. If you guys look back on the front of your sheet, that first example we did, x minus 2 is a factor of that binomial. And by the way, we could just factor the binomial, all right? Let me just take a second. We know how to factor. Let's take this thing and factor it, right? 2x and x. We got a positive 6. We're going to have to use a negative times a negative. Either -1 times -6 or -2 times -3. If I go what? Negative 2 here and negative 3, isn't that the factoring of that? Wasn't x minus 2 a factor of that quadratic? It was, right? And we knew it was when we got a 0 remainder. However, if you look at the second example, just leave that up there. If you look at this second example, if you tried to factor this, first off, you're going to try 4x and x, or you're going to try 2x and 2x, right? Two possibilities. Let's see. 1, you got to use -1 and -1. There's no choice. Does that even work? You get a -2 and a -2. That's a -4 in the middle? No. You got to use -1 and -1. A -4 and a -1 is a -5. That doesn't even factor. There are no binomial factors to this polynomial. If we were solving it, we used the quadratic equation, right? So is x plus 1 a factor of that? Nope, because look, you get an 8 remainder, right? All right, so the remainder factor tells us how to find the remainder, and the factor theorem tells us if it's a factor. Okay? The remainder theorem tells us how to find the remainder, and the factor theorem says if the remainder is 0, then it is a factor. We put those two together and we can figure out if something's a factor or not. So then you'll start getting questions like this. Is x minus 3 a factor of this? For it to be a factor, you're looking for what? Say it if you know it. For it to be a factor, what are you going to expect to get? A remainder of 0, right? So that's what you're after, a remainder of 0. Okay, so if it's an x minus 3, right, then we have to do p of 3. Do you agree? So go ahead and solve that. See what you get for a remainder. Right, and hopefully you agree, yes, it is a factor. Right, you should have gotten 27 minus 21 minus 6. 27 minus 27 is 0. So, hey, that is a factor. Great. But that's a quadratic. We could have factored that thing anyhow. But look at example B. Oh, we got a polynomial now. All right, we don't have a quadratic. We got a polynomial. And this is where we're heading. Third degree and above. We got to find the factors of something third degree or above, right? And the way to do that is to use the remainder theorem to then use the factor theorem to see if we get a 0 remainder to find out if we have a factor or not. Okay, so go ahead and try B. I left empty what you're supposed to put in to the parentheses. Go ahead and fill in the parentheses and solve B. Be careful with your positives and negatives. You can use your calculator if you need to. Is it a factor? Yes or no? Just looking for a yes/no answer here. Is it a factor? Yes or no? By the way, if it's yes, you got to do everything right to get a 0. If it's no, you can make mistakes and get the wrong remainder and say no, right? As long as it's not a 0, you're going to say no. So you could even do wrong stuff and get it right if the answer is no. But to be honest with you, we're not after the no's. We're after the yeses. That's what we want. We want yeses. Is this one a yes or no? It is a no, right? And did you get negative 67? Maybe you didn't and still said no. You should have gotten negative 67. Negative 67? That's not right. That's not even close, is it? Let's see, what does this say? 14, so that's, yeah, it's negative 67. Huh? Negative 67. But again, you could get it wrong and get it correct if it's not a factor. So in your homework, you're going to be asked, is this a factor? And you're just going to use the factor theorem. You're going to do exactly what you did right now to figure out if it's a factor or not. Okay? You're going to place the value in. So this all started with, hopefully you used negative 3, right? And be careful when you're cubing negative 3, you get a negative 27. That's why I left that step in there. Negative times a negative is a positive, times a negative is a negative. However, when you squared it, you got a positive. That's why I left that in there, so be careful. Questions? Andrew? No, remember, when it's a negative in front, you use the exact value. In this one, you have two ways of looking at it. You can look at it this way to figure out to use a negative 3, or you can set it equal to 0 and solve the little equation to figure out to use a negative 3. Again, some people just say, okay, if this is a plus, then it's the opposite, it's a negative 3. Okay? Anybody else? All right, that's all, folks. And